Everyone is talking about AI agents. Companies are funding them, developers are building them, and analysts are calling them the next platform shift. But if you ask most people to explain how an AI agent actually works under the hood, the answer gets vague fast. This video gives you the real mechanics of how AI agents work, step by step. First, let's be clear about what an AI agent is not. A standard chatbot takes your message, generates a response, and stops. There is no memory of past conversations, no ability to take actions in the world, and no plan. It is a very sophisticated autocomplete. An AI agent is something different. An AI agent is a system built around a language model that can perceive its environment, reason about what to do next, take actions, observe the results of those actions, and then repeat that cycle until a goal is reached. That loop, perceive, reason, act, observe, is the engine behind every agent system you will encounter. The perception step is about inputs. An agent can receive text, but modern agents can also receive structured data, the output of code, web search results, database queries, or even images, depending on the underlying model. The richer the inputs the agent can process, the more useful it becomes. Reasoning is handled by the language model at the center of the agent. The model reads the current state of the task, the history of what has happened so far, and any instructions it was given at the start. Then it decides what to do next. This decision is not magic. It is pattern matching at an enormous scale, shaped by training and guided by a system prompt. The action step is where things get interesting. An agent can produce text as its output, but it can also call tools. A tool is any function or API the agent has been given access to. That might be a web search, a code interpreter, a database lookup, a calendar API, or an email service. The agent decides which tool to call and what arguments to pass in. After the agent takes an action, the result comes back as an observation. That observation gets added to the agent's context, and the loop starts again. The model reads the new state and decides whether the goal has been achieved or whether another action is needed. This is called a react loop, short for reasoning and acting, and it is the foundation most popular frameworks are built on. Now, let's talk about memory, because this is one of the most misunderstood parts of AI agent design. There are 4 types of memory an agent can use. The first is in-context memory, which is simply everything inside the active context window. It is fast but limited in size, and it disappears when the session ends. The second type is external memory, which means storing information in a database outside the model and retrieving it when needed. Vector databases are commonly used here. The agent converts information into numerical embeddings and stores them. When the agent needs relevant context, it searches the database and pulls in the most relevant chunks. This is how agents handle long-running tasks that exceed the context window. The third type is in-weights memory, which is the knowledge baked into the model during training. The model already knows a huge amount about the world without needing to look anything up. The limitation is that this knowledge has a cutoff date and cannot be updated without retraining. The fourth type is in-cache memory, which is a computational shortcut. When a model has already processed a long prompt, the intermediate computations can be saved and reused instead of recalculated from scratch. This makes agents faster and cheaper to run on repeated or overlapping tasks. Planning is where the agent loop becomes something more powerful. Instead of just deciding the next single action, a planning agent tries to decompose a complex goal into a sequence of subtasks. One common approach is called chain of thought, where the model reasons step by step before committing to an action. Another approach is tree of thought, where the model explores multiple possible paths before choosing the best one. Some frameworks go further with a technique called reflection, where the agent reviews its own outputs and scores them before proceeding. If the output does not meet the criteria the agent set for itself, it tries again. This self-correction loop is what allows agents to catch simple errors that a single-shot model would miss entirely. Multi-agent systems add another layer on top of this. Instead of one agent trying to handle everything, you have multiple specialized agents working in parallel or in sequence. One agent might be responsible for research, another for writing, another for fact-checking. An orchestrator agent manages the overall workflow and routes tasks to the right specialist. The coordination between agents introduces real challenges. Agents need to share context without overloading each other. They need protocols for handing off tasks. And the system needs to handle failures gracefully when one agent in the chain produces bad output. This is an active area of research, and the reason most production multi-agent systems still require significant human oversight. Now for the honest part. Current AI agents fail in predictable ways. The most common failure is called hallucination propagation, where an early reasoning error gets embedded in the agent's context and influences every decision that follows. Because the model trusts its own prior output, the error compounds instead of correcting. Agents also struggle with very long task horizons. The further out the plan extends, the more likely the agent is to drift from the original goal. Context windows have grown dramatically, but they are still finite, and once the relevant information scrolls out of range, performance drops sharply. Tool reliability is another real problem. When an agent calls an external API and gets an unexpected response, many current agents fail to recover gracefully. The model was trained on clean examples, and real-world APIs are messy. Robust error handling in agent pipelines is still largely a human engineering problem. Security is worth mentioning because it is often overlooked in early builds. Agents that can browse the web or read files are vulnerable to prompt injection, where malicious content in the environment tries to hijack the agent's instructions. This is a serious concern for any agent with access to sensitive systems. So, where does this leave someone who wants to start building? The best starting point is to pick one framework, learn it deeply, and build a small agent with a limited set of tools on a task you actually care about. LangChain, Llama Index, and the OpenAI Assistants API are all reasonable places to start depending on your background. Understanding the perception, reasoning, action loop, the 4 memory types, and the failure modes covered in this video will give you a frame for evaluating every framework and every new agent product that gets announced. The vocabulary changes, but the underlying architecture stays consistent. If this breakdown was useful, hit the like button because it tells the algorithm this kind of content is worth showing to more people. Subscribe if you want a new video on applied AI every week. Next up, we are going to look at RAG systems, how retrieval augmented generation works, and why it is the most practical way to give any AI product accurate, up-to-date knowledge.